Y bienvenidos a esta conferencia magistral que será impartida por el profesor Shiban Koul, en representación, digamos, y con el patrocinio de IEEE, en atención precisamente a nuestro distinguido invitado, y si no tienen mayor inconveniente, el resto de la sesión lo vamos a manejar totalmente en inglés. So, welcome again and good evening, everyone. Welcome to this distinguished instructor workshop that will be presented by Professor Shiban Koul. And thanks to the sponsorship of the IEEE MTTS, the Microwave Theory and Technology Society of the IEEE, in collaboration with the MTTS Guadalajara section chapter, and also in collaboration with the Department of Electronics, Systems and Informatics here at ITESO. So my name is Jose Ernesto Rayas Sanchez. I'm the coordinator for Latin America of MTTS, and I'm also, of course, a professor here, an emeritus professor in the department, in this same department at ITESO. And along with Dr. Edna Moreno, who is seated there, she is the current MTTS chapter, Guadalajara chapter chair. She's the chair of the Guadalajara chapter of MTTS. So both of us will be chairing this session. So, without any further ado, let me introduce Professor Shiban Koul. He received the Bachelor of Technology degree in Electrical Engineering from the Regional Engineering College, the Master of Technology degree and the PhD degree in Microengineering from the Indian Institute of Technology, Delhi, in India. He is currently an honorary professor at the same institution. His research interests include many fields, but particularly RF MEMS, high-frequency wireless communications, microwave passive and active circuits, millimeter and submillimeter wave integrated circuit design, local body area networks, flexible and wearable electronics, medical applications of sub-terahertz waves, among many others. He has a prolific research. He has been a prolific researcher and consultant, as you just saw in the synopsis and the biography in the flyer, with more than 625 research papers, more than 23 books, including book chapters and e-books, as well as 26 patents, among other outstanding scholar achievements. Professor Shiban Koul is a life fellow of IEEE, a distinguished microwave lecturer, and a speaker bureau lecturer of MTTS, and he has been the recipient of many impressive awards, international awards. So welcome again, Professor Koul. It is our pleasure and an honor to have you here in Guadalajara. Thanks for being with us. And please feel at home, and the floor is yours.
I mean, you may not trust me, but that's important because I've been in this area for the last 40 years. And most of the work which I will show you is done by our students. So it's not difficult. Only thing is you have to keep an open mind. And to help you, the slides are here. I've given it to Jose. You can copy the slides. You can take the PDF file so that whenever you have time, you can go through it. And at the end of the slides, you have my email. In case you get stuck up, you need a book, you need e-book, write to me. I'll send it to you. So the title of this talk, I'm going to go a little bit faster because of the time constraint. The backbone is transmission line. Whether you design high-speed, high-frequency integrated circuit, transmission line is the backbone. So when I was doing masters in '79, I had a lady boss. She said, you work on transmission lines. And I remember some of the tricks she showed me. Today, I'm able to publish those tricks. So you have to learn how to actually manipulate things. So many things are not there in the books, so you have to learn it on your own, and then some packaging structures and PCBs designs for the industry. And as Jose said, I'm a life fellow, and I've been a past distinguished lecturer. I spent 5 years as a MTT distinguished lecturer. Currently, for 2 years, I'm the Electromagnetic Compatibility Society distinguished lecturer, and also Region 10 coordinator, which is Asia Pacific for antenna propagation. So AP, microwave, MTT, same thing, AMC, they're all same things. Now let's look at electronic circuit development, past, present, and future. Past PCB designs were simple. They're very simple. We used to do it in the lab. Due to less population of components and lower frequency of operation, megahertz, you can make a PCB in your own lab. All functionalities of a microcontroller could be realized using a single chip. We used to have just a single chip with power supply, decoupling capacitors integrated. So most important was electromagnetic interference problem. We didn't want the circuit to generate electromagnetic interference. More attention than what is presently looked at is SI, signal integrity. So it has become very, very important, SI and PI, which is power integrity. These are the two important parameters. But when you look at present and future, all of you have mobile phones. Everybody wants to use 10 megabits per second, 100 megabits per second. You want to play video games on your thing. So with IoT revolution, applications have become physically smaller, complex, need interfaces between controllers and external memories. There are hundreds of memories now. You would like to feed them, so you have to have traces. A lot of effects come when you design a multi-layer PCB. Need to study the effect of high data rates on the interfaces. Even if you have a small solder connect, it's no longer a lump element, it's a transmission line. Transmission line effects give rise to SI and PI issues. These are, I think, whole industry now is looking at how to design circuits which have better signal integrity, power integrity issues. So these are the reasons why in future, when you go to industry, I think you will be working in these areas. Let's start with what is AMI. AMI is the interference caused by electromagnetic disturbance that affects the performance of the device. Often manifests in undesirable noise, and this may lead to a lot of problems in the electronic RF systems. And there are several types of EMI. I won't go into detail. Conducted, common mode EMI, differential mode EMI, radiated EMI. If you Google, you will get the definition of each one of them. It's in the slides here. Then what's EMC, which is electromagnetic compatibility? If you have the equipment, EMC is a measure of any device's ability to operate in intended its shared environment, while at the same time not affecting the ability of other equipment within the environment. Electromagnetic compatibility of electronic RF device is basically ability to properly work in presence of electromagnetic radiation. Everywhere there's radiation, mobile phones, TV towers, everywhere. So the ability to not generate, in addition, it should not generate additional electromagnetic interference from the equipment, which is certified as EMC. Just to give you, this is a ship. Of course, this incident happened when I was not born, 1954. I was born right after this incident. To meet the system requirements, we need EMC. EMC problems can sometimes have hazardous effect. There were switches on this. They triggered on their own. And the missiles fired on the ship itself, killing 160 people. There are two of them. You should look at the literature. USS Forrestal and HMS Sheffield, both of them got destroyed by simple EMC problem because the switches got triggered and it destroyed the systems itself. Then what's SI? Signal integrity is the quality of an electrical signal. You transmit a pulse, you would like to have the same pulse at the receiver. Through a printed circuit board, it could be single layer, it could be multi-layer, and measure of how much signal degrades from the driver to receiver. You have a driver here, you have a memory here. How much signal degrades in this path? And we think that we are using an interconnect. It's a transmission line when you go to very high frequency. The problem is not a major concern at low frequencies, but it is very, very important for PCB design when you go to high speed and high frequency. And signal distortion takes place because of these factors. Signal characteristics get distorted. If it's a square wave, you should get square wave at the receiver. Interconnect effects, even if it's a 1 millimeter interconnect at 100 gigahertz is a big transmission line. Impedance mismatch, reflections, crosstalk, propagation delay, attenuation, ground bounce, AMI. All these distort the signal, and what you expect at the receiver, you don't get it. So you need to design, use HFSS, CST to manipulate things so that you get basically a much better integrated signal at the receiver. What is PI? Is power integrity in a printed circuit board is the practice of ensuring that boards, you have several networks, power distribution network. At each point you need 1.2 volt, you want 1.1 volt, you want 1.6 volt. Depending on the topology of the network, you want exact stable voltage. So you need stable voltage, you need clean return path, you don't need any interference. A poorly designed power distribution network can lead to unpredictable performance and AMI issues. And these are some of the factors which affect power integrity. Switch mode power supply, electromagnetic interference from other sources, DC power loss, and heat. So in many multi-layered circuits, you have basically signal lines, power lines running simultaneously. So you have to design in such a way it doesn't couple, it doesn't actually create more AMI problems. Now let's look into the first course on electromagnetics, the transmission line. This is a transmission line. We say this is a lumped component if length of this transmission line in terms of wavelength is very, very small. What is very, very small? Typically 20, less than 20. L by lambda less than 20. Then we say this is pure lumped element. But if wavelength becomes smaller, 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 frequency increases, this length is huge in terms of wavelength. So we cannot consider this as a lumped element, but for analysis what we do, we break this into small delta Z, delta Z, delta Z, but delta Z much, 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 much less than lambda. So each delta Z has an equivalent circuit, resistor, capacitor, conductance, and capacitance and inductance. And multiply by delta Z, which is the length of this, we can calculate resistance, inductance, capacitance. This is basically the equivalent circuit of a small piece of delta Z. But we need to analyze the actual transmission line, which is not lumped. So what we do, we go to Kirchhoff's voltage law, Kirchhoff's current law, take this small segment, feed current IZT here, IZ plus delta ZT, this is voltage, this is current, write these equations, KVL, KCL. I'm sure many of you wouldn't have forgotten this. These simple equations. This gives basically the voltages and this is the current. Then combine these two together, we get a differential equation, d square Vz by dz square equal to gamma square Vz. This gives you voltage variation along the line. This gives you current variation along the line. These are simple differential equations. You can solve them. Vz is V0 plus e raised to minus gamma z. E raised to minus gamma z is wave traveling in the plus z direction. If the line is matched, you will have only one directional wave, no reflection. But in practice, there are reflections. So e raised to gamma z is wave traveling in the minus z. So general solution is this. For current, it is like this. It's V0 plus is amplitude of the forward wave, V0 minus is amplitude. Then we can calculate from this gamma, what is the propagation constant, is attenuation constant plus phase constant J beta. This is in terms of R, L, C, and frequency. Then we can get attenuation in Nepers, phase constant, and impedance of the line is given by R plus J omega L by gamma, or gamma by G plus J omega C. It's under root R plus J omega L by G plus J omega C. Please remember, there's an omega term coming. We normally take impedance, 50 ohm, 100 ohm. Impedance is never real. Strictly speaking, it's never real because we have R plus J omega L. If R is 0, G is 0, then it becomes real. So now let's look at two cases, distortionless case. We don't want distortion. If I put R by L equal to G by C, if I manipulate these parameters, ensures that different frequency components in the signal suffer same attenuation, they also travel with same velocity. This is what we ideally want. We don't want any distortion. Then second parameter is dispersion. A general lossy line has phase constant, which is not a linear function of frequency. Different frequency components of the signal, if you take a pulse has infinite number of frequencies. Each frequency travels with a different velocity along the line with different velocity. The overall signal at the receiver, they suffers dispersion. These are very important parameters which one should understand. Now let's look at the transmission line. This is an interconnect whose impedance is R0, small interconnect of length L, and this is terminated by resistor RL. I take real impedance. The reflection from this termination is RL minus R0 by RL plus R0. Now, if RL is equal to R0, there's no reflection. There's no reflection back. But if RL is greater than R0, gamma is positive, reflection coefficient is positive. If RL is less than R0, gamma is negative. So depending on the termination, you're connecting it to a memory. What is the input impedance of the memory? Some signal will come back. So depending on what gamma you will have a standing wave on this particular transmission line. So you'll have voltage standing wave, return loss, all those parameters are considered. So it's very, very important concept. So signal integrity issues due to interfaces and high data rates. This is your signal. At the receiver, you will get a distorted signal basically because of the loss of the transmission line. And this is basically going to result in intersymbol interference. So you will not be able to recall because it falls in a different bin. The second thing is this is a common printed circuit transmission line called microstrip. This is dielectric, ground clear, two conductors. One trace, another trace. You may have in practice 30 traces in a practical circuit. Now how close the trace is. So if some of you are familiar, this type of transmission line is called coupled microstrip line. It has two impedances. If I apply 1 volt here, 1 volt here, the impedance given is called even mode impedance. If I apply 1 volt here, minus 1 volt here, it's called odd mode impedance. The coupling from one trace to another trace is given by ZOE, even mode impedance minus odd mode impedance plus even mode impedance. You can quickly calculate, depending on the gap, how much is the coupling from this conductor to this conductor. So when you have 32 traces, you have to draw the layout in such a way that they don't couple beyond some point. It will couple 100 dB down, that's good, but you don't want 2 dB coupling. So then it's of no use. So this is one major challenge. Now let's look at review the transmission lines, what are there available in the literature. Conventional transmission line, this is conductor, red one is conductor, this homogeneous dielectric, and it's called stripline. Stripline has a property that is wavelength is equal to free space wavelength by under root of epsilon r. This is epsilon r. So you get shorter traces than microstrip, produces less crosstalk, lower EMI because it's a shielded structure. If you take microstrip, which is most commonly used, it's very easy to fabricate because you have printed circuit board fabrication only in one layer, produces more crosstalk and more EMI because if there's a conductor here, it will couple to it. So EMI radiation in this one is there. If you bend this conductor, it will radiate, couple to another circuit. So microstrip is very easy to fabricate. So the solution is, industry does, they put another dielectric on top, it's called embedded microstrip. Now this trace is better protected from exposure to environment. High density of components and interfaces due to narrower trace with approximately 30% reduction in the size. EMI radiation is better than microstrip, but it's not zero. So when you design a circuit, you should know which transmission line I should start. You design a circuit at megahertz, you design a circuit at gigahertz, you design at 10 gigahertz, we design circuits at 1000 gigahertz. What media should I use before you go into HFSS, CST? Because there's a calculator. HFSS is a calculator. But input has to be very, if you go garbage in, garbage out. If you give correct in, you'll get correct output. So it's very, very important. So HFSS, CST, they're not all. You have to feed correct inputs to them. So this is one set of transmission lines. The second set of transmission line is called coplanar transmission lines. Now we don't have ground here. We have conductor, conductor. This is center. This is signal line. These are two ground conductors. It's everything on same side. Now you want to mount an active device, you can mount between ground and the signal line. So basic coplanar waveguide has signal line in the center, semi-infinite ground lines. Direct integration of high frequency active passive components here. Slight reduction in radiation compared with microstrip, wider effective width compared with, these are all the advantages. In general, if you use coplanar lines, we can put a ground also here, or grounded coplanar line. This is coplanar strip and we use only two. In general, rotating density increases using grounded coplanar line, but still, this is not the best line at very high frequency. And if you are going to make an integrated circuit where you would like to use probe station to probe these signals, coplanar waveguide is the only set. It's a microstrip, you cannot use the probing. Now the third set of transmission line, in fact, to be honest with you, this is what my guide had, my lady who came from Harvard, she said you work on this in 1979. She gave me this problem and I have 2 publications in IEEE on this line. What this is the same microstrip. I create a small air gap. It's very easy to create air gap. Reduction, the moment you create air gap, this is 9, this is 1. Effective permittivity is close to 1.5. So you have reduction in effective permittivity, convenient dimensions at millimeter because wavelength is large now. So you can use at high frequencies isolation improvement by adjusting the air gap. If you adjust the air gap, put another conductor here, you can have practically 50 dB coupling between the two conductors by simply adjusting the air gap. Why we do that? Because there are two velocities on parallel coupled line called even mode velocities, odd mode velocities. By adjusting the gap, they get equalized and the isolation becomes practically infinite. So this is a line where you can get, NASA used this to get 90 dB directional couplers, which is not possible in microstrip. Then you invert the substrate, it becomes an inverted microstrip. You can see now this is almost a cavity. Effective permittivity is close to 1 because most of the field is in air. Tray is better protected from exposure because there's a dielectric on top. This is a very, very useful transmission line. Very easily we can use it to build circuits up to 100 gigahertz. Very easy. Later I'll show you a filter at 60 gigahertz. Then you put it in a metal enclosure like this. It's called trapped inverted microstrip. Trace is better protected from exposure to environment. As the fields are trapped in the channel, less AMI, practically no AMI, radiation and discontinuities are not there. Extremely high isolation because it's an isolated structure. So you get an idea which transmission line has what advantages. Now the next class of transmission line, this is my favorite, is suspended substrate line. This is basically a thin dielectric suspended in a channel like this. Many people when they look at it, oh, it's very complicated, especially from industry. It's very difficult to fabricate, very simple to fabricate. Dielectric substrate suspended in metallic enclosure. Traces can be printed on one side or both sides because this will give you a lot of capacitance. If you want a capacitance, we can have trace on top, another trace on bottom. We get large capacitance, which is epsilon A by D. Traces can be printed on both sides. Thin dielectric with low permittivity are preferred. Wide range of impedances. In microstrip, you cannot go above 100 ohms. To realize an inductor, we need 150, 200, 300 ohms. Only this transmission line, I can realize 300 ohms. No AMI radiation, absolutely, it is shielded. Since most of the field is in air, losses are considerably reduced. Quality factor 500, microstrip is 60 to 70. That's the difference. This is suitable for also circuits when we require environment, minus 55 to 70 degrees. Nothing changes here because effective permittivity is 1. This is the medium, which is useful up to 300 gigahertz. Close your eyes, you can build all circuits at up to 300 gigahertz in this transmission line. In our lab, we have built everything up to 140 gigahertz. I'll show you some of the circuits later. Now look at it. People think, oh, it must be very complicated to design. No, it's not design. You need just one formula. If you look at this structure, this is the conventional transverse electromagnetic mode. This is E field, and this is the H field. TEM mode, what is there in the coaxial line. Now, we want to have only channel dimensions so that only this mode propagates. What is the next higher order mode? Is a waveguide mode, which is TE10 type mode. These are documented in the literature. The cutoff frequency of this mode is given by V0 by 2c, velocity of light. 2c is this dimension, dB, 1 by epsilon r. So what you need to do, select dimensions so that this mode is not propagating. So you can use the structure up to that frequency, push this mode up and up based on these dimensions. For example, if I take D 0.254, epsilon r 2.22, selecting C 2.35, B 1.2, ensures that you can work up to 60 gigahertz. Shrink these dimensions, you can work at 140 gigahertz. Shrink it, you will work at 300 gigahertz. Very convenient to make one formula. You don't need Maxwell's equation, you don't need anything. Now, this is how we fabricate it. If you want to do it low frequency, but there are better techniques later I'll show you. So you have to suspend it here. Many students tell me, say, it's so complicated to suspend this dielectric. No, take a block, metal block, take this dielectric, print the circuit, another metal block, sandwich them together. This is how this structure looks like. This is low frequency, but high frequency, there are different techniques. Now this is what has to be done in future. This is called substrate integrated suspended substrate line, SISL. And later I'll show you a book. First book on this transmission line came from China in April. I'll show you the picture so that you can buy it and start using it. This is an excellent medium. Just now you saw I use metallic housings. I don't need metallic housing. Now you can use 5 substrates, 10 ground places. These are different layers in this structure. PTH for forming SSL cavity, useful for fabricating SMT components and subsystems up to sub-terahertz communication feasible using this medium. This is the only medium you can do it, and industry can use standard techniques, PCB techniques to fabricate this and create these air cavities. Large number of air cavities can be created using this particular structure. Now, signal integrity improvement using SI-SL. Reducing signal loss, it's practically no loss. Shielding, it is perfectly shielding. Improved impedance matching. Reduced parasitic capacitance in this structure. Improved signal isolation. One conductor to another conductor is infinite isolation. Enhanced thermal management because everything is air. Reduced radiation loss, there is no radiation. This is an ideal medium for high-speed integrated circuits. And I'm not going to read these, they are already with you. The slides will be with you, you can read them. Now, another set of transmission lines is if you're using silicon, for example, micromachined transmission line. We take a silicon substrate, unfortunately its dielectric constant is very high, it's lossy substrate. Nobody uses silicon normally, unless it is high dielectric constant and resistivity is very high. Both micromachined, microstrip. So what you do, you have the silicon substrate, you put it in a solution of potassium hydroxide, it creates a cavity like this. It's called an air cavity. It's called, process is called bulk micromachining. It's very easy. In the chemistry lab, you can do it. So you can create essentially air structure, but using silicon, very precise. Both micromachined, microstrip, and coplanar lines can be used. Effective permittivity of this structure is close to 1 because it's all air. This is just 5 micron for support, and this is 200 microns. Loss is considerably lower as microstrip. Wide range of impedance are possible by adjusting cavity. Circuit dimensions, especially at millimeter wave frequencies, are at least 4 to 5 times than the conventional microstrip. Due to air cavity, high quality circuits are possible. Hundreds of papers are there to make circuits up to 100, 200 gigahertz using this technique. And we can integrate it with CMOS. It is very, very easy. Now, another technology, polystrate technology, is basically same as suspended if you see it, but process is different. It's a microelectronics process. This is a dielectric, and this is a conductor. This is air. So this is a new enabling architecture for future 3-dimensional millimeter wave circuits, perfectly shielded, low loss, pure transverse electromagnetic mode. It's 20 times smaller than conventional coaxial lines, 80 times the trace spacing, better than microstrip, 85 times. Suitable for products in the range 10 to 200 gigahertz, ultra low dispersion, very low loss per wavelength, extremely high isolation, very low radiation from the circuits, enabling highly dense interconnects. So this process has been perfected, and you can have 14 such layers in this direction, multiple layers in this direction. You can have complete radar developed on a silicon wafer using this technology, complete radar. So how the process is, it's like this. We take the substrate, we put the strata and then planarize it. Then after the planarizing, we create the dielectric studs, metalize it, and then remove this portion middle. So you have the suspended lines like this. This is very, very interesting technology, highly compact. You can get very small circuit, complete subsystem using this technology with all AMI problems gone, shielding problems gone, circuit isolation gone. This is the ultimate, and you can use microelectronics process to fabricate this kind of thing. The next one is, recessed ground transmission line. This is one of our PhD students. What she does, this is a microstrip line. She creates a small recess under this. How is it created? We create a hole in the metal plate through laser. On top of it, we put a microstrip antenna. And this is the antenna structure. Now you can see, when you don't have recess, you get a 30 dB return loss. And when you put recess, you get about 45 dB return loss. By simply putting a recess, the quality factor improves and the gain improves by 4 or 5 dBi. People who are familiar with CMOS circuits, one of the problems is integrated antennas. Antennas have minus 1 dBi, minus 2 dBi loss. If you can create in this process this air gap under the antenna, you will get at least 4 to 5 dBi gain. So this is very, very important, and you can make other circuits also. I haven't done anything. I just created an air gap. Small air gap, you can see at 60 gigahertz is few millimeter by few millimeter air gap. It's not seen even from top, but this is a full IEEE transaction paper on antenna propagation for this concept. So this is very, very important to learn these concepts. The other very important transmission line, unknown to many of the students, and this non-radiative dielectric guide transmission line. So this consists of metal, this is a dielectric. Now there's no conductor here. So How we excite it? We excite E parallel to the metal plates. And if you put E parallel to metal plates and put B less than lambda by 2, then this mode, which is transverse magnetic mode, is not propagating. So it's cut off. The moment I introduce this dielectric, here this condition B less than lambda 0 by 2 is not satisfied, so it propagates wherever there is a dielectric. You bend the dielectric like this, it propagates only along the dielectric, nothing in air. So even if you have another dielectric guide very close, it doesn't couple. So absolute high isolation using this one, and you just use two formulas to design it. 26 to 100 gigahertz, very low loss, no crosstalk, absolutely low cost technology, low AMI radiation. It has all the advantages of a transmission line. Now, how we fabricate circuits is very easy. You don't need actually a machine also. Before that, I will tell you another transmission line. It is spook surface plasmon polytron. It's a complicated name, SSPP transmission line. About 8-9 years back, we started working in this transmission line. What this is, these are basically, this SPP is surface wave that propagate at the interface between a dielectric and metal. If you have a dielectric and a metal, you can show that these SSP lines are there. This concept has come from optics. But two gentlemen, Pendry and Vidal, they showed that if we take a dielectric and create in this one holes, or you create some periodic structure, it's exactly same as creating metal, and it has same surface wave. So the structure looks like this. It is for next generation ultra broadband communication. Lower transmission loss, very good isolation, less loss, crosstalk, and minimum AMI radiation. So this is the transmission line. This is microstrip. In between, we use this corrugated structure. Different types of corrugations can be used. And you can see the transmission is practically zero. Return loss is very good. So this line is called SSPP line. And you see every day 10 or 15 papers are appearing in various journals in this transmission line. Very simple to fabricate. So let me just show you, if this is a microstrip 2 traces spaced at 4 millimeter, you see what happens. As frequency increases, the coupling from this to this increases. Practically all power gets coupled to this line. Very poor isolation in microstrip. But if you take same 4 millimeter, use SSP line, you can see it is better than about 15 dB isolation in this particular course. So this is very, very good as far as the isolation is concerned. And you can look at the CST micro studio, create a coupler here, feed signal here, it comes out only this port, very little here, nothing, negligible. In microstrip, if you feed signal here, lot of it gets coupled to this particular port. So isolation in microstrip circuits, very, very poor compared with SSP line. So this is a very, very useful line. You should look at literature. Practically up to terahertz, all circuits can be made using this SSP line. Extremely good for sensing application, wearable devices, textile integrated circuits into your jacket. This is one very important transmission line. Now let's look at multi-layer PCB and vias. Now you have hundreds of lines going from one particular, let's say, source to memories. We cannot put all these traces on one layer. It's impossible because of the gap. So what do? You bring out the trace down, another layer, trace down, another layer, trace down, another layer. So you'll have a structure like this. You have multiple vias. So this is a through via, this is not plated via, this is a different type of blind via. So various types of vias are possible. What happens with the via? You have a signal line here. Let's say it goes to this and you connect here. This via gives inductance. The moment there is inductance, there is a mismatch. So what you need to do? You need to modify this via. So the general technique to modify this via is like this. What you do, you create antipad via, which is basically you drill a bigger hole and create a capacitance here. And this is an inductance plus capacitance. This is the equivalent circuit. Adjust in CST studio the inductance and the dimensions of this antipad so that you know reflections are minimized. But it's very, very complex because you have hundreds of vias, 8 to 20 layers structure. And this is design has to be done very, very efficiently. But if you go much higher frequency, these kind of interconnects will not work. So you have to look at alternative ways of interconnecting the structures. So what are those interconnecting ways? This is other high frequency interfaces. We use DuPont substrates, and then we can create holes like this. This is called low temperature co-fired ceramic technology. We can create antenna here, we can create power amplifiers here, we can create multiple circuits here. So this is one of the technology. We can create liquid crystal polymer technology. We create in layer 1 digital circuit, layer 2 phase shifter, layer 3 interposer layer, general amplifier, power amplifier, antenna feed. It's a combined small cube using liquid crystal polymer. The interfaces are very good. Or you can take gallium arsenide wafers and design it in such a way that you don't have to connect. They are basically simply bonded, and the interconnects are very minimum, and this technology reduces the circuit size drastically, and the performance up to 100, 200, 300 gigahertz you can very easily achieve. Circuits have been made using all these technologies. Another very important technology, you can see how researchers work, is anisotropic conductive adhesive based high frequency interface. You want an interface between this conductor and this conductor, this conductor, this conductor, this conductor, this conductor in multi-layer PCB. So what you do, you don't physically do a through hole. So what you do, you use gold-coated ferromagnetic particles and push them inside. These are gold-coated ferromagnetic particles. Now, the advantage of this is that we apply magnetic field and align them. They get automatically aligned between the conductor, next conductor, conductor, next conductor, conductor, next conductor. Once it is cured, it becomes a permanent transition, high frequency transition, and you measure it 0 to 80 gigahertz. It works less than 1 dB loss. So this is the technology what people are now using to do this. This is a replacement for flip chip bonding of devices, wafers at very, very high frequency. Since I'm giving you the source also, so you can actually read a little bit more about these things. Now, when you look at packaging, for example, this is your PCB chip and your heat sink, there will be a lot of AMI radiation. So how do we suppress it? We don't want too much bulky material to be put there. So I mentioned about SSP line. So we can do an ultra-thin SSP-based sheet for suppressing microwave radiated emission in system and package modules. Whenever you have a system and package module, you just introduce a very thin, it's 1 micron, 2 micron thin sheet. But this is based on SSPP line. Please remember, this is the very current research, 2023 April. Just few months back, this kind of research is reported by a Taiwanese company. They're actually using it. So what you do, you create a concentric circle on polyamide-based material. These are basically SSP line. I showed you that different gratings. Pull out one of them, it is like this. Arrange these gratings into a ring like this. These are multiple different orientation gratings, and this is analyzed on HFSS or CST microwave stereo. And you can see a particular pattern gives you almost 100% compared with all other techniques which are reported, almost 100% absorption by using a simple thin, ultra-thin absorption sheet to suppress entire AMI. So very good for chip industry development, putting this kind of thing. Now the other techniques are, of course, you can use a metallic mesh over a chip. We can do also a material design. We can use carbon nanotube based. We are doing a lot of work, and by April you'll have the first book on electromagnetic absorbers using carbon nanotubes, where from our group we are getting. So we can coat these using this ultra thin material, or suppose you have a networking equipment, you have a box, so we can create a box with a lot of patterns you see here. These are resistors inside. These are polarization absorbers. A lot of work is going on in polarization absorber. So there's an electromagnetic wave incident on this box. It will not penetrate. It will reflect it. So these are very lightweight. So a lot of such things can be used for electromagnetic interference shielding. Now let me just give you quickly some components which you can do using these newer transmission lines. Let's look at, you want to design a double balance mixer using microstrip line, slot line. So this is from Terman book. I don't know how many of you know Radio Engineering by Terman. It is 4 years before I was born, but the book is still there in the library. This is the double balance mixer, lumped circuit. This is a transformer. I have tap, local oscillator, radio frequency, 4 diodes here. And this works as a double balance mixer, but it will not work at 30 gigahertz. It will not work at 100 gigahertz. So what you need to do, we need to translate it. So what we do, we use backside here, this is slot line, this is metal removed. Top is microstrip line, and then we design these radial steps in such a way that this becomes, and then join them, and this is the center tap, this is the center tap. This replaces this balloon. This is a balloon, 18 to 40 gigahertz. So I have one balloon, another balloon. This is local oscillator radio frequency balloons. This white one you see, they are basically slot lines at the back. Put 4 diodes here, and in 2 days you can have the mixer. Test it for 7 to 8 dB conversion loss from 18 to 40 gigahertz. Put it in EG. This kind of mixer takes hardly about $10 is the diode cost, but you can sell it for $1,000. The company is selling these kind of things. So that's the kind of thing, if you know the design techniques, you can actually use this for developing very high performance components. The next thing is, it's 18 to 40. So somebody approached us, can you make it, this balloon up to 100 gigahertz? We said yes. So we can make the same balloon work up to now 100 plus gigahertz. And what we get as an academician is this, US patent, full US patent on this thing. Now we can sell it to a company, we can make now mixers using this kind of technology very easily. Now let's look at, I mentioned about trapped inverted microstrip. So you want to design a bandpass filter, you know nothing. You don't know electromagnetics, nothing. You want to design this bandpass filter tomorrow. So what do? You take the structural dimensions and create this gap in HFSS or CST Micro Studio, analyze it for gap capacitance and parallel predicate. This you can extract from scattering parameters when you analyze it. So you get CGCP. From there, you go to Mathai's handbook and design the filter number of sections, create these gaps here. And this is the tested 60 gigahertz filter. You can go up to 100 very easily here. You put a bed of plated through holes here so that there's no electromagnetic radiation coming out of the structure. So you can do a lot of such structures depending on your requirement and integrate it with multi-layer PCB. You want to design a much higher frequency filter, 140 gigahertz filter, looks very complicated. So this is the structure. The dimensions are in millimeter, please remember. 0.4 millimeter, think in your mind, 0.4 millimeter is how much. So the layout of this structure is, this is the conductor, this is the filter layout. G1, G2, G1, to G1. So what you do, analyze one of the gaps, take gap, scattering parameter, convert them into a parameter called J inverter from Mathai's book, and these are the dimensions for the gaps. And then, since it's 140 gigahertz, you use a waveguide transition here, your filter is done. So this is how the filter looks like in our lab. You can see these are the very small RT Dürer circuit. This is the transition, put this metal cover on top. This is 140 gigahertz filter. This is narrowband. This is 3 gigahertz bandwidth. This is 10 gigahertz bandwidth. So you don't need to know Maxwell's equation. You can just master CST HFSS and know the filter design technique. Then you can very easily make such components. You can also make a crossbar mixer. You have 2 diodes here. You feed local oscillator here. This is a probe which picks up the local oscillator signal, feeds it to the mixer diodes, and this is on bottom side. As I said, in suspended, you can put conductor here also. It's on top side. It's automatically a DC block. Impedance matching network and low pass filter. You can have conversion loss of this mixer is about 12 dB at 140 gigahertz. You can make very novel components using this particular technology. Now let's look at this SI-SL technology. This is really very versatile technology. You want to make a frequency tripler. So this is the layout of a circuit, DC bias, RF choke. This is the transition, band stop, matching network, and diode chain matching network, and then you have a high frequency transition. So various layers, as I showed you, have different components, and you can see 73 gigahertz, return loss is very good, and when it is tripled, you get 220. So if you have a problem of making a high frequency source, you can do it in the lab by using this particular technology. And this is a simple multi-layer PCB, 1, 2, 3, 4, 5, 6, 7 layer PCB. Integrate a waveguide at 73, integrate a waveguide at 220 gigahertz. You have this particular kind of circuit. Now, let me give you an example of handheld transceivers. You can hook on a computer, and at a couple of kilometers, you can play video games, very high-speed transceiver. It consists of a gun oscillator, circulator, ASK modulator. You don't need special modulation technique. And then you have an antenna which transmits, another antenna receives, and you have a local oscillator thing. It mixes, and you get intermediate frequency. Then you process it, and you can display it on your computer. Now first, let us look at how we make the oscillator. As I said, you remember, E has to be parallel to the plates, I said earlier. So you put a metal plate and put gun diode here so that it generates E parallel to these 2 plates. use a resonator to couple it to a dielectric guide, and use dielectric resonator to stabilize the oscillation. These are excellent. Transmitter oscillator 35.11, receiver oscillator 34.9. It's done by students by hand. You don't need spatial machining technique because the tolerances here are not that great. Once you have the oscillators ready, then you need a mixer. So how do you do a mixer? You have the dielectric guide, another dielectric, you bend it. It doesn't radiate, as I said. So there's no radiation from bends. So you can bend it as much as possible, and this is 3 dB coupler. 3 dB power comes here. So radio frequency signal and RF LO signal, these are single-ended mixers, and then you take the IF output. This is the conversion loss of the mixer. This is how a single-ended mixer is a diode here, Schottky diode. So once this is done, then you integrate all of it together. Now you look at how beautiful it looks like. This is an MDT issue. This is 50 millimeter by 50 millimeter transmitter. This is the gun oscillator. Couple it to the dielectric guide, circulator. This is ASK modulator. And it transmits 15 dB gain antennas by tapering this dielectric. Then this will be covered by a metal plate. Then on the receiver side, you receive the signal here. Then this again a coupler. Go to the single-ended mixer. This is the local oscillator. And take the IF output, 153 megahertz IF. And then you process, and you can play video games. Very high-speed links, and this is just about few $100. You can make it in your own lab. This can be done at 35, 60, 90 gigahertz. Very easy technology, but many people in the industry don't know about it, so they don't use it. Now, I said micromachine circuits. If you take silicon and make an elliptic filter, this is how it looks like, very congested. The moment I create a gap at the back, you see how the circuit size becomes bigger, and the loss is high Q, loss is considerably less, sharpness is very good. So you can make multiplexers using this technology by simply dipping the silicon substrate in potassium hydroxide and controlling the depth of the cavity. So this another area which is called now 5G, 6G is becoming very, very important. So you want to develop tunable filters. So this is micro electromechanical system tunable filter. You can see here, these are cantilever beams over a transmission line, and these are the series switches, 4 series switches, 4 cantilever switches. You analyze this, you can make a very nice filter, and you can tune it by applying DC bias to move these cantilevers up and down. So you can see the response of this filter shifts by applying different bias voltage. You can shift the bandwidth, you can shift the skirt, everything is possible. And there's a full IEEE transaction paper which we published in 2020. So we don't need to tune anything. It's just by applying a bias to these cantilevers, the conductors get shifted up and down, capacitance changes, resonant frequency changes. So this has a lot of commercial applications. Similarly, you can make an antenna on silicon, create a cavity at the back. You see a 35 gigahertz antenna, simulated, and measured results are perfectly okay in this one. So there's enormous kind of things you can do using these kind of technologies. Now this is a phase shifter which is needed. So you can see we developed a SP16T switch. So 16 paths here, and this is the delay line, 16 delay lines. So you get basically 4-bit phase shifter. It's IEEE Journal of Micro Electromechanical thing. This is the world's smallest phase shifter reported, 3.62 by 3.37. And this is a patent in US we grant. We're trying to commercialize it. And we can make a very small phase shifter for mobile application, for many other applications, by simply switching the transmission lines using SP16T switch. Now, coming to the high end, which is polystrator circuits, we can have multi-layers. So on layer number 1, we can put all active circuits, diplexers, cavity resonators. Layer number 2, we can put feed networks. Layer number 3 is antennas. Layer number 4, we can assemble all of it together. This is a very complex circuit which we can realize on one silicon wafer. The entire radar, active electronic scan radar, is just on a piece of silicon. One silicon piece is complete radar. And this was demonstrated last time at the IMS in US by a company. So we did research for many, many years, and so there are several books. This is the first book which we wrote in '88, very useful for multi-layer, multi-conductor, multi-layer structures. You can write a MATLAB code and generate your own data. You don't need to depend on the software. A lot of structures are there. in these books. If somebody is interested, you can email to me. I can send it to you both e or hard copy. We wrote a 700-page book for the John Wiley, which is complete description of the dielectric guide structures. And I have some copies of these books. This is the first book available from Arctic House on SISL. I have not written it. It's by a Chinese. And very useful for designing multi-layered structures. And then we have ourselves written micromachined circuits, all micromachined components starting from switches, phase shifters, LC resonators, oscillators are covered in these two books. As I said, I still have many books with me, and I'll be glad to give it to you, anything. I have e-copies also, but a request is a must. And send a request, I'll send it to you. Of course, I'll send to Professor so that you can go through it in detail. But this is 40 years of work we have gone through in different areas. So it's not possible to understand it in 1 hour's time. But since I'm leaving the slides here, go through it. Maybe something wherever you are working, doing a project, it may fit in. You don't need to do everything again. You can do it. And there are also too many applications of this electromagnetic and terahertz in biomedical area. That's my another talk. Sometimes when Jose invites me again, I give that talk. But you can join the region 1 to 9 on 25th and 28th is virtual. So we'll be there, please attend. So you will see how many applications of terahertz are there for medical diagnostic and cure of diseases, including cancer treatment. That's in that talk. So please have a look at it. He will send the link to you. You can actually look at it. There are three speakers. Now, coming to conclusion and suggestion, whether you like it or not, AMI, SI problems exist everywhere. And I presented a review of transmission line for application in micro to sub-terahertz. We have used all of them for making practical circuits. Present-day engineers, you say I'm an artificial intelligence person, I'm an electromagnetics person, I'm an antenna person. Those days are gone. You have to dirty your hands in multiple fields. For example, basic electromagnetics, antenna engineering, microelectronics, computer science, artificial intelligence, machine learning, cloud computing, mechanical engineering, material science, biomedical engineering, EMI suppression techniques, EMC, and SI. You have to learn many, many things depending on one thing. And you need to join microtheory techniques. I don't know how many of you are the members. Antenna propagation, EMC, they are same. GRSS is another society. And learn megahertz to terahertz technology, including EMI, EMC challenges. And IEEE, basically, if you look at what they want, IEEE, why you want to become a member, we have to serve humanity. So together we need to serve humanity, develop a gadget which will help monitor my blood pressure remotely. Develop a gadget which will measure my blood glucose without pricking. We have done it. In the second talk, we are covering that. And future will demand, of course, besides high-speed integrated circuits, low-cost variable wireless devices. This will be everywhere at very high speeds, and people are tending now to sub-terahertz to terahertz frequencies. So learn these techniques. One of the things which I mentioned, SSP, which is very new, excellent transmission line for the same integrated circuits, but it has a lot of advantages. Please look at SSP sensors. They're extremely useful for blood glucose measurement and cancer detection and other type of things. So with this, I conclude the talk, of course, 5 minutes late, because we started 5 minutes late. Thank you for your attention. This is my email, s.k.koul@ieee.org. And of course, this will be in your slide. So you can email to me after 21st, because I'm reaching India on 21st. Right now, I'm going to San Francisco. And be sure, 90% cases, I'll send you the book and e-book. There's no problem. Nothing mine. It's all we have to share. That's the ultimate objective of the life. And objective of the IEEE, serve humanity. All of us should serve humanity. Thank you very much.